Hello, welcome. My name is Brandon, and today we have another problem to solve. So I'm going to read the problem first so we can go ahead and get started and see how we're going to solve this. We have a container with a total volume of zero point 0.1 meters cubed, and it contains 1 kilogram of liquid water with air in the headspace at 101.325 kilopascals. And the starting temperature is 298 kelvins. Then it's sealed. To what temperature should this container be raised to such that the final pressure is 200 kilopascals? We're going to repeat this calculation where the total volume of the container is unknown and where we have zero point 0.3 moles of water vapor desired in the vapor phase at the same final pressure. So just to get started, what we need to do is let's first just see what data we have. So let me add a code right here. So we have our total volume, and that is going to be equal to 0.1, and then we have our the weight of our water, so our water weight, and that is going to be equal to 1 kilogram. And then next we have our initial pressure measured in pascals. So we're just going to put pressure of our initial, and that is going to be equal to 101.325 pascals. And then we have our initial temperature, and that is going to be designated as Ti, and that is going to be equal to 298 kelvins. And we know what our final pressure should be, such as we want it to equal 200 kilopascals. So 10 to the 2 times 10 to the 5th, measured in pascals. And we have our R constant. Just going to slide that in up here. We're going to name that R equals 8.314. All right, perfect. So what we need to do first is we have our data, input it. Let me go ahead and enter here. What we want to do is we're going to use a tool today. So we have tools that we can use, and it's going to make this entire problem a whole lot easier for us. We're using Google Colaboratory, and we're using Python as our interface for coding. So let's import. And this is going to be I don't think it likes the name I gave it. Tools.ke. Simple names and package. You can manually install deficiency names. All right. So this allows us to find different properties of whatever element or liquid that we choose actually. So I'm going to demonstrate that here by let's find some properties of water. And what's so cool about this is we can actually, I'll show you real quick. This is our data that we imported as Chem Tools. And what it does is it's an entire database of different critical temperatures, boiling points, just different properties of a lot of different liquids and mixtures in here. So let's just look at carbon dioxide. We see we have molecular weight, critical temperature, and we can actually import this right into our data by using our tools. So we just import it. Just want to show you that. So let's say I wanted to figure out what the vapor pressure of water is at a certain temperature. We're going to put P dot PVAP, and our initial temperature is 298, so I'll just sub in TI right there. What it gives back is that at temperature 298 kelvins, our partial temperature of water is actually 3,155 pascals. So that is just one example of how we can use this into our coding. So what we get to do next is we actually get to draw on the whiteboard, my favorite part. Let me make sure y'all can see everything. All right. So what we have is, one second. Is that okay? So we know that PV is equal to NR. PV is equal to NR2. So what we're trying to find is our final temperature? Yeah, we're trying to find our final temperature. But we can't do that initially. All right, so in order to find our final temperature, we first need to see what we're looking for. So, and our knowns and unknowns. What we know is that we have our initial pressure and our final pressure, and we can use our different temperatures to find the pressure of water within our closed container. But what we don't know is we don't know the pressure of our air, and that's going to change between our different temperatures. So what we need to do first is figure out an equation to find our pressure of air. Because eventually we're going to have our total pressure is going to equal our pressure of H2O plus our pressure of air. Now, to find pressure, it is equal to P equals nRT over V. Our problem with that is when finding the pressure of air, we don't actually know the moles of air in our initial or our final phase. So what we're going to solve for first is our N, which is our moles of air. So let me just get rid of that and rewrite this equation. We have N, that was terrible. N equals PV over RT. Make sure we're all seeing the same thing. Perfect. All right. And so now that we're going to find our moles, we need to figure out our pressure. So we have a container sealed, and it has water and air in it. All right. So we're going to have different pressures. We're going to have our partial pressure of air and a partial pressure of water. And we're going to have our volume of air equal our total volume subtracted by just our volume of water. Okay? So let me rewrite that by our moles of air is equal to our initial pressure minus our pressure of water at 298 kelvins. So we have our P, and now our V, our volume of air, is equal to our total volume minus our volume of water. Divided by our gas constant and our initial temperature. All right. So now that that's out of the way, let's go find our moles of air. So what we're going to do is actually make that screen back up so I can maybe able to see that. So moles of air is going to be equal to our pressure, which is PI, minus our partial pressure of water, and we've actually already solved that once, haven't we? You see how our chem properties tool is really going to come in handy right here? We don't have to go find it. It's already in our equation. It's already in our data, and we're able to just implement it into our coding equations. So P dot PVAP of our initial temperature should probably add quotations, multiplied by our volume total total volume minus the volume of water. Now the volume of water in our problem is going to be, we have 1 kilograms of liquid water. So we actually don't know our volume of water yet. What we do know is that we have 1 kilograms. So if we have 1 kilograms, then we know how to find our volume of water. So we know that density equals mass over volume. So our volume of water is equal to density over mass. So what we need to figure out now is, what's the density of water? Well, we don't have to even know. We don't have to go figure it out. What we get to do is we get to use our tools in our code and actually just plug it in. Let me find my code here. Let's get rid of that. And so density is mass over volume, so volume equals density divided by mass. Right? No, did that one wrong. Someone should have told me. We did that wrong. I knew it sounded wrong in my head. What we need to do is we get volume equals VP equals mass over our density. All right, now we can put it into our equation. Almost caught myself. All right, so we have our water weight, which is 1 kilogram. besides that as well. Water weight divided by, so what we're going to do is we're going to find the density of water. That's going to be P dot RHOL at a temperature of initial temperature. And so now that we have our initial pressure minus our pressure of water at our initial temperature, that is going to be multiplied by our volume total. So we get to add one more parentheses. Is this not right? We need to add one more. Or, maybe there's just too many. There, that goes to that. That one and that one. This one. So, back out. That one goes to that one. That one goes to that one. And that one goes to that one. So, that's our top of the equation. And all of that is going to be divided by R times our initial temperature. All right, perfect. In air is going to be equal to, so we have 40 moles of air at the beginning of our equation. So now that we have an equation for PV nRT that involves all of our units for our initial temperature, we actually get to find the root of various equations, and this is going to be able to allow us to find our final temperature. So what we're going to do is we're going to set up a whole new equation. PEQ of X. Yeah. Fingers are glitching today. And we're going to use this equation to find our final temperature. So that is going to be equal to X. Equal to X. What we get to do next is import more equations. So if we look here, we have our, let me get rid of some of this. Oops. Almost drew on my on the code. Where is it at? So we have our our volume of vapor is going to be equal to our V total minus our volume of water. And that's going to give us how much air is in the volume. The equations that we get to use, we have already set up for ourselves. It's just a matter of rearranging everything. So we are looking for our final temperature, and we already have our volume total, and we already know the volume of liquid water using our density. So we're going to look for our vapor pressure. The volume of vapor is going to be equal to our V total our total volume subtracted by, we've already used it once. Go ahead and copy and paste. Doesn't want the two. Our water weight divided by P dot RHOL of our, this time, final temperature, so that we're using our final temperature in different equations. And what we want to find next is our partial vapor pressure. So PW, we have not used that yet, no we have not, is going to be equal to our partial vapor pressure of water, evap, at our final temperature. And then we also would like to know our partial pressure of air at our final temperature. So P air is going to be equal to N air times our R times our final temperature divided by our vapor pressure, volume of vapor. Okay, and we want it to return out PW plus P air minus our final pressure, which is 200,000 pascals from the beginning. Okay, what we get to do next is we have our, what would you say, different equations using our final temperature, but we get to set them equal to each other to find our root values, which is going to give us a answer for TF. So to find our root, we're going to actually import the root function. So we are going to need to go to up here and from Skype.optimize, we are going to import root. Yes. And what we get to do next is ROT, and from our list of equations, and we need to put an initial guess. What would be a good guess? We're just going to use our initial temperature, so it has something that it can't be lower than, if that makes sense. So TI, shift enter. Would you look at that? Would you look at that? All right, what we get to do next after finding our final temperature of 58 kelvins is, let me go ahead and erase the board. What we need to find is we need to find our, in our new equation, or in our new problem actually, we are looking for our final temperature again, and we are also contemplating that we have 0.3 moles of water vapor desired in our end result. So 0.3 moles of water vapor is desired in the vapor phase at the same final pressure. So our same final pressure is going to be 200,000 pascals, but this time we're going to use a little bit of different PV and RT to figure out what we need to get, all right? So what we're going to do first is we already have our initial, our water weight, 1 kilogram still. Our initial pressure is the same, and our initial temperature is the same. So we get to use those still. We still know our moles of air, but This time water vapor has left and it's zero point 0.3 moles of it. So what we get to do is we need to change our vapor, our volume of vapor pressure, because it's not the same. Our volume of vapor pressure is no longer going to be what it was, because we know we have to add on to that 0.3 moles of vapor pressure. But first, what we need to do is we need to get that 0.3 moles into a number that we can actually use. All right. So let me start off with, we have 0.3 moles, and we need to get that into molecular weight. So we're going to multiply that by, hydrogen is 1.09, so there's 2 hydrogens, 1 oxygen, H2O. So 16 plus 2 is going to give us 18.02, and then it's all going to be over 1,000, so that we can get our mass of our vapor. All right, and we get to use the same equation. We already have it written out, so we might as well copy and paste it. That's one thing I do love to do. Saves us a lot of time and trouble. Let's go down here, Control V. This time though, we actually have another missing variable. That other missing variable is going to be our V total. We don't know our V total because we're actually adding 0.3 into the vapor phase. And adding that 0.3 into the vapor phase is going to give us a different volume in the very end. The volume is going to remain consistent, but how we find that volume is going to be different. Let me forewarning. V total is going to equal X 1. All right. And so how we're finding that volume is going to be different. So that is because our vapor, our volume of vapor is going to be an additional 0.3 moles of vapor. So what we need to do is we need to go to our VVAP equation, and let me draw this out for you, all right? So we have our initial weight of water. It's 3 kilograms. Let me make sure about that. I don't want to steer you on the wrong ship. 1 kilogram, sorry. Keep doing that. No, bring that back up. Our initial weight of water is 1 kilogram. And technical difficulties today. And we need to have 0.3 moles of it gone from our 1 kilogram. And then we're going to just label this right now as D. And then our vapor pressure of water, the D desired that we're going to take away, is then going to be divided by our density of water. That is because volume is equal to mass over density. So if you're following me right now, this is where we're getting at. We have 1 kilogram of water, and we're going to actually take out of that 0.3 moles because it's going to be turned into water vapor. So then we only have what is left divided by our density to give us our volume of water. And then we're going to use our total volume minus our volume of water to give us the volume of vapor that is going to be in the air. Our volume of vapor that is going to be in the air. Yep, all right, that's perfect. So we're going to label, we have our water weight, which is 1 kilogram, and that's going to be subtracted by our moles of water desired, our D, and that is going to be multiplied by the molecular weight of water, once again, so P dot MW, which is 18.02, and then that's going to be divided by 1,000, and then divided by our density. I hope that makes sense for everybody. Sorry if I was a little confusing. And what we have next is we're going to have our partial pressure of water is going to equal PVAP at TF all over again. And so I'll make sure they're separate. All right. And we're going to have our partial pressure of air, as always, equal to PV and RT. And our moles of vapor is going to be equal to, let me show you. So if we have PV equals nRT, then we're looking for our moles. So we have PV over RT, and that is going to equal our moles of water that is turned into vapor. So our partial pressure of water times our volume of vapor go ahead and put the parentheses divided by our final temperature. And we're going to have two equations, which is why that did not work, because we didn't put the other equation in here. So this is going to be our vapor, the amount of vapor minus our desired amount of vapor pressure, which is our 0.3 moles, because we want to add more to it. So they're supposed to equal each other, but we have to underscore capital D. So now we get to use our root equation one more time. And I didn't signify how much Vn is actually going to be, so v vap underscore d is going to equal 0.3. And now we need to do our root of our PQ. We don't want to get this mixed up with the one from before, so we're going to add a 2 right there. Shift enter. PQ2, comma space. And let's see what our initial guess is going to be. We're going to need 2 guesses, so let's start with TI. And for our volume, our last volume was 0.1. Let's go with 0.1 as well. Yes. 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 So it says this time we have our final temperature of 285 and a volume of 0.488. Now, what we get to do next is actually my favorite part, I would say. I'm actually going to explain to you all the van der Waals equation of state, which allows us to find our critical temperatures and our critical pressures, which are invaluable. They are, if you can find those, you can know everything about a liquid, a compound, or of the such. So first off, let me show you how important they are, okay? If you go to any of these, you're going, well, I hope it pops up. Critical temperature, critical pressure, critical volume. At the top of the list, right under molecular weight and formula name. That's how you know they're essential. So what we're going to do first is I'm going to write out the equation of, let me make this bigger because we're just working with the whiteboard here, okay? Let's get rid of this. And hopefully, if I make this bigger, it gets bigger for you all. Is that how that works? Nope. How about now? Give me 1 second. All right, here we go. Our code is down here, and now we get to work with our van der Waals equation. So let me start this out for you all. So we have P every time. Oof, can't do that, so I'll get to just do it. P V equals N R T. That is true, but whenever we have a specific volume, our moles becomes 1, and so we get PV equals RT when N is equal to 1, giving us a V, which is specific volume. All right, and now let's backtrack a little bit. Let's just say we're finding pressures, all right, because that's what we can always measure out volume, we can always test the temperature, but finding the pressure of something is not always the easiest thing to do, especially in closed containers. So we're going to equal, P is going to equal RT over V. Now, this is a very, very simplified equation, all right, because if you think about it, whenever you have a container, closed container, right, and you have these particles inside, right? Well, our volume V is accounting for the entirety, the total. But what we're not accounting for is the volume of our different little molecules within our container. So what van der Waals done was he enabled us a constant that we're allowed to subtract from our V total, which is equal to how much space our compound is taking up within our volume. So we're just going to label this constant B, all right? And now that gives us our, you see what I'm saying? Equals that. Volume of that gives us this right here. So let me just go ahead and erase this. And now we get to do our V minus B. Okay, so that's our first constant. Our next constant is actually going to be minus A over V squared. And what our A is going to do, it basically just gives us a correction for the different interactions between our molecules within our volume. So from here, what we're going to do is I'm going to rewrite all this, because what we have here is we have our equation of state, which is PV equals RT for a specific volume and a specific mole ratio, which is just of 1. And so I'm going to clear the canvas and write P equals RT over V minus B minus A over B squared, where B is accounting for our molecular weight within our volume, the space it takes up, and A is just going to be a constant within that helps with the interactions between each molecule within our container. So what we're going to do now is we're actually going to find the differential of this pressure so that we can figure out our constants. We all know that constants turn 0 after so many differential equations. So what we're going to do now is we're going to find d of P over dV. So that's going to equal, we have V minus B, so V to the negative 1 is going to be negative V over squared. So we have negative RT over, this R is just 8.31 K, and temperature is going to remain constant when finding our pressure. So they're just constants. V minus B squared, and since V's on the bottom over here, plus 2A over V cubed. And what we're going to do next is we're actually going to find the second derivative. So we have d2P over dV squared is going to equal A2RT over V minus B cubed minus 3 times 2 equals 6, 6A over our volume quadrupled to the 4th. So you might be asking yourself, what are we going to do now? Well, at this point, we would sub in our critical values, and we have a critical temperature, a critical volume, and a critical pressure. Let me make sure I said that right. Temperature, pressure, volume. Yep. All right. Just want to make sure. And so we're going to evaluate dP at R, TC, PC, and VC. It's going to be equal to 0, and same with D2 of P. Make sure everyone can see this. All right, perfect. And how we're going to do that is we're going to set them equal to each other since they both equal to 0. So if I have 2 RT equals 6A over e to the 4 over first by taking away the 2. That becomes 3, divide by 2. And next, what we see is our first derivative is equal to 0. But what we can do is 2a over v cubed equals rt over v minus v squared. So what we get to do is we get to take each of these and multiply by its respective side. So if we have 2a v cubed, we're going to flip it, and we're going to have v cubed over 2a multiplied by the right side of our equation, and we're going to have v minus b squared over rt multiplied by the left side of our equation. This is going to cancel out. And so we have an equation where one side is equal to the other side. We're going to find the reciprocal of it and then multiply each respective side by that side. And now in the end, we're going to get RT over RT, RT over RT, V minus B, and negative 1 is equal to 3 over 2 V A. Let's make sure we get that right real quick. No. Our A is going to be gone. Now let's flip both sides again. We get find our reciprocal. V minus B equals 2 over 3 V. And if we have a negative B equals to V minus 2 over 3 V, we get negative B equals negative 1 over 3 V. So B is equal to 1/3 our critical volume, which in retrospect accounts to a lot of volume within a container if we're at our critical point. Yeah, that's actually a substantial amount of volume. So now we're going to put this back into our equation so we can find our A. So what we're going to do is we're going to plug in our b actually into our first derivative. So we're going to have negative RT, it's not even, negative RT over V minus 1/3 V, C, critical temperatures out here, everything's critical value, is equal to a negative 2A over V cubed. So what we're going to do first, let's just squared. Just going to make this negative RT. 1 minus 1/3 is 2/3. 2/3 squared is 4 over 9. 2/3, 2 squared is 4. V, C, equal to negative 2A V cubed. Properties. So now we have 9 V cubed RT over 4 equal to 2A. Divide by 2. We get an 8. And A is equal to that. Let's do some manipulation. VC over VC, we get 9 critical volume squared times our R constant times our critical temperature over 8. And so we have our constants, A, which is factoring in relative push and pull from each ion and each molecule within our compound, and B, factoring in at the critical volume how much each molecular weight or compound is actually taking up within our container that is unaccounted for. So we have a more specialized van der Waals PV and RT equation. And now what I'm going to do is I'm going to rewrite all this for you so that we can see our final project of this equation. So in the end, we have our critical pressure is equal to R, or critical T, over VC minus 1/3 VC minus 9VC squared There we have it, folks. Thank you for your time today. I hope you enjoyed the video. Let me know if you have any comments.